Okay, so in our last couple of classes, because believe it or not, we are into our last couple of classes, I want to revisit the concept of the integral a little bit. The concept of integral, the volume of a set. We saw before, when we did the Riemann integral, that we can't integrate everything. Some functions we cannot integrate. Some sets do not have a well-defined volume. There's different ways than the Riemann integral to define integral. So the next more popular way is the concept of the Lebesgue integral. So I want to spend the last couple classes giving what we'll call a very brief overview / introduction to the Lebesgue integral. Please do not consider this a fully rigorous introduction, but I want to give some highlights. I want to show how we can now integrate some functions that we could not integrate before. And then I will plan to put one bonus question on the final exam related to this content. Okay, so there'll be 6 questions on the final exam, each worth 10 points, graded out of 50 points. So a bonus question that you don't have to do to ace the final exam, but maybe this is a little bit of an incentive. Once again, I will not be proving every statement that I make here. If you want to see this in more detail, consider this also a preview for taking 645 or something next year if you want. Okay. So we want a concept. We're probably not going to do a general integral today. Today we're going to talk about the concept of the size or the volume of a set, and I'm going to only work on the real line, so one dimension. This generalizes to Rn just fine, but let's stay in one dimension just to keep the ideas as clean as possible. So we want to start with the concept of the size of a set. So okay, so we're going to come up with something that we're going to call, well, eventually we'll try to call it a measure, which is a function that operates on sets. And you stick in a set, it spits out some non-negative number that tells you something about how big this set is. So the domain of our function is going to be just all possible subsets of the reals to start with. We can have sets that are, of course, infinitely big, and we're going to allow that. So if our domain is all possible subsets of R, including the whole real line, presumably the size of the whole real line, if we're trying to do something that is somehow consistent with our intuition, I'm bringing us back to a world where we have a little bit of intuition now. We want infinity to be an allowed output. So our possible outputs will live in this set, R plus, which is going to be the reals or infinity. This is called the extended reals. So we're going to start by thinking about some properties that we would like our concept of the size of a set to have. And we're going to call a function that has these properties an outer measure to start with. And then later we'll talk about how we go from outer measure to a measure. So an outer measure, right, is some kind of function. Okay, so let's call the function mu. So the domain of mu is subsets of R, so it takes as an input a set, and then it spits out a value in the extended reals. And we're going to propose a few reasonable properties that we think the size of a set should satisfy. One is that the empty set has no size to it. So the empty set is going to have outer measure equal to 0. Another probably nice property is if one set is contained inside another set, then the smaller set should have smaller size than the bigger set that contains it. Okay, so if A is contained in B, then mu of A should be less than or equal to mu of B. So we have some sort of ordering going on. And then lastly, what happens if we take the union of a bunch of sets? So let's say we take the union of a bunch of sets and we want to know the size of the result. Well, of course, this should presumably be at most the sum of the sizes of the individual sets, but of course there could also be overlap happening in here, right? I mean, maybe all of these A's are the same. So it's probably reasonable to ask that this is at most equal to the sum, the size of the individual sets. This is called subadditivity. If they're disjoint or just equal, that's a great question. Hold that thought. We're going to come back to that. Okay, so aside from your question, which is the obvious one to ask, what happens if the sets are disjoint, which I'm going to come back to, but not quite yet. These properties are reasonable for the concept for the size of a set, and there's plenty of functions we could come up with that do this. So I guess a kind of a boring concept would just be to say all sets have size 0. But that satisfies these properties. It's not very interesting. It's probably not very useful. But one can do this. Another thing that we could try is to count how many elements are in our set. This is called the counting measure. So we'll say that this is equal to n if the set A contains n elements. Okay, for some finite n, and infinity otherwise. Okay, that's maybe a slightly more useful set, but maybe not so interesting when we're working with the reals, because a lot of the sets we care about on the reals, for example, if we just want a straightforward interval, because we do lots of things with intervals, interval has infinitely many elements in it. So there's kind of no real way of distinguishing most interesting sets using this measure. So here's a more interesting one. And what we'd like, I guess what we'd like is to sort of recover something that's consistent with what we've done in the past, the Jordan measure, right? We said the Jordan measure worked. It kind of fit our intuition of what should go on. But there were some things it just wasn't powerful enough to do. So what we'd like is something that still gives the same answer as everything what we had before, but is a little more powerful. And this is the concept of the Lebesgue outer measure. So the Lebesgue outer measure works maybe kind of similar to what we've seen before. We're going to take our set and try to cover it with little intervals, and then add up the length of the intervals. There are a couple important differences here. So let me leave a little space here. We're going to look at summing up intervals, where we're expecting that A is contained in the union of all of these intervals. And okay, these points are ordered. So, in some sense, these intervals could overlap. We may have tons of overlap even, right? So if I'm doing this, adding up the lengths of all these intervals, I should be getting something that's too big, bigger than the size of my actual set. So what I want to do is take the smallest possible result, the infimum of all of these. And maybe that gives me something that is a reasonable size for my set. So this is called the Lebesgue outer measure. So again, this has a similar flavor to the Jordan content of a set, where that's essentially what we were doing, covering things in little intervals and adding them up. So what's different? Why is this going to have the chance of doing something different than the Jordan content? So, how is this different from the Jordan content? You look like you're thinking of suggesting something.
So, thinking that this would work for infinite, like unbounded sets?
This would work for unbounded sets, sure. There's nothing in here that asks my set to be bounded. We're happy for this to spit out a value of infinity. So indeed, I can stick any set I want in here, right? And this quantity, I can, any set I want in here, if there's something I can cover it with, I can cover it with all of the reals, for example. This quantity is certainly bounded below because it's bigger than or equal to 0. So if I have a collection of real numbers that are bounded below, the infimum is well defined. So actually, I can put any set I want in here. No matter how ridiculous the set, I can put it in here and get an answer. So that's one important observation. This is defined for all subsets of the reals. Any other important differences you see here between this and between, what happens when we do a Riemann integral over a set?
We also take the value of the function.
What's that?
Of the Riemann, we don't.
Well, in the Riemann integral, we take the value of a function, but here, let's say my function is 1. When we're doing this, the measure, the Jordan measure of a set, we take the function 1. But somehow this is not quite the same.
Finite.
Yeah, that's it, exactly. In a Riemann integral, we always have a finite sum here. We take our domain, we partition it into finitely many subintervals, and we sum them up. Here, I'm allowing infinitely many intervals, and that means, in particular, they could get arbitrarily small or arbitrarily big, right? In a Riemann sum, a fixed Riemann sum, we just have some minimum size and maximum size, but that's not true here. And that's going to be a key difference that lets us get a handle on some weirder looking sets. So here we allow infinitely many terms in the sum. Okay, and you can check, yeah.
So does that mean that this measure is defined in much wider sense?
So this, yeah, as I've written, this is defined for a much larger domain. So I guess when we talked about the Jordan content, we said that was defined on sets whose boundary had 0 content, right? So it was a subset of capital X, which isn't there anymore. This is, as I've written it now, is actually defined on all of capital X. Now, hold tight, there's still going to be a problem. But yes, this has a much bigger domain right now. And it still will, even when we start out problems, have a bigger domain. And one can check that, without too much difficulty, that this satisfies all the properties of an outer measure. Okay, and for example, just to try to ground ourselves in reality a little bit, if we take a typical interval, And we look at all possible coverings of this with intervals and look at the infimum. And the infimum will be b minus a. It's always good to do sanity checks along the way where you're doing something new. Have I broken something important? Try it out on easy examples. So this is good. We get the kind of result we expect for the usual length of an interval. Now, let's try a slightly different set that we had some trouble with before. So let's let A be the rationals between, say, 0 and 1. Do you remember what the Jordan content of this set was? I think 1. So remember, do you remember what the boundary of this set was? 0 to 1. The boundary of the set was this whole interval. Okay. The volume of this is 1, and we said if the boundary is not 0, then the Jordan content of A is simply not defined. Okay, so this is a set that we could not come up with the size of before. It was simply inaccessible to us using our previous tools. It's not an entirely ridiculous set to want to know some things about, though. Now we think, or we made a bold claim, that this object is defined for all possible subsets of R, which means we should be able to get a number out of it, even when we plug in this set. So let's try to figure out what that number is. So I made this claim, and we'll see why this is important for us getting a number out. The fact that we are allowed to use infinitely many things to cover it, right? Even though, right, this stuff, this isn't a set that has bounded. It's a bounded set, but it will still be important to us that I can actually use infinitely many level intervals. So one thing we do know about this is it's countable, right? I can put it in one-to-one correspondence with the counting numbers. This is going to be important. So this set is countable. So we can find a one-to-one correspondence between this set and the natural numbers. Okay, so we'll just let these be Q1. I mean, I can even make it explicit. Maybe Q1 is something that has denominator 2. Then I start trying to get a handle on everything that has denominator 3. Everything that has denominator 4. Right, skipping 2 out of 4, of course, because that already showed up. And I keep going, and I get a list of all possible rationals that live in my set. So we get a list of all the elements in A. Right, in other words, another way to say this is A is simply the union of all of these little singletons. Now I want to try to define the outer measure somehow. So that means I need to start covering this set with a lot of intervals. Now, we know if I had to do this with finitely many intervals, I'm going to end up covering the whole interval from 0 to 1. I'm just going to have to because, you know, if I leave out any little subinterval of it, there's always rationals in there. So if I have to use finitely many intervals, we're covering the entire interval 0 to 1. But I don't have to use finitely many intervals. I can use infinitely many intervals, and that's what I'm going to do. In fact, to each one of these guys, I'm going to put an interval around it. Now, if I just say, all right, I pick an epsilon and I put an interval of width epsilon around each of these, even if epsilon is small, if there's infinitely many of them, the sum of these is going to add up to infinity. We probably don't want the length of this to be infinity. You know, this is contained in the interval 0 to 1, so its size should be less than or equal to 1. That's one of the properties of an outer measure, subadditivity. So we've got to do something more clever. I'm going to put an interval around each of these, but they're not all going to be the same size. So I'm going to put a small interval around this, and then a smaller interval around this, and still smaller around this, and keep going, keep getting smaller and smaller, so that even though there are infinitely many of these, somehow the size of these should add up to be finite. Okay, so let's pick a small epsilon. All right, now I need to create my AIs and BIs. So what I'm going to do is say, let's let A1, B1 be half minus epsilon, Q1 minus epsilon, to Q1 plus epsilon. Let me make it over epsilon over 2, so this has length epsilon. Okay, again, I can't keep going using the same length for all my intervals because infinitely many tiny epsilons are going to still sum to infinity. So I have to start shrinking things. So next I'm going to say, well, let's let the next one, why don't I cut its size in half? Sorry, Q2. Okay, and the length of the interval gets cut in half. And then I keep going like this, and in general, I say let's let AI, BI be the interval from QI minus epsilon over 2 to the I to QI plus epsilon over 2 to the I. Okay, it's epsilon over 2 to the I minus 1. Okay, and because I could put these in a list, I could put them in a one-to-one correspondence with the naturals, right? All of the rational numbers will show up here somewhere. So I've got an interval covering every one of my rationals. So if I take the union of all of these intervals, they're certainly going to cover my entire set. Because my entire set is nothing but the union of all these numbers.
Can't you use the same epsilon for all of them? Is it because you're taking infinitely many of them?
Because I'd be taking infinitely many of them, I can't use the same epsilon. Exactly. I'd add up. Because when I go to compute my outer measure, I have to sum up all of these. So I'd have epsilon plus epsilon plus epsilon plus epsilon. And it doesn't matter how small epsilon is. There's infinitely many of them. And that gets big. Okay, so we definitely have now that A, right, which was again was just the union of all of these QIs. Now by construction, I think we've used this trick before of just, we're going to cover a bunch of things, let's just stick one interval around everything. By construction, this is now contained in the union of all of these AIBIs. Okay, so, I mean, the definition of the outer measure says we have to look at all possible coverings. I've looked at one. So summing up these interval lengths is going to give me an upper bound on my possible outer measure, right? The outer measure was the infimum of all of these. I've picked one, which is either going to give me something that's equal to the infimum or it's bigger than the infimum. Okay, so from the definition, okay, of the Lebesgue outer measure as an infimum, okay, we know that the size of this set is going to be less than or equal to the sum of these interval lengths. Okay, we know what these interval lengths are. They're epsilon over 2 to different powers. Let me, to make this a little clean, epsilon over 2 to the I. So this is 2 times the sum of epsilon over 2 to the i's. All right, and now, okay, I have infinitely many things I'm summing up, but of course the terms are getting smaller, and we've set them up in such a way that I can actually do this sum exactly, right? This is just a geometric series. So, of course, I could have picked my intervals to get smaller at a different rate, but I picked something that would be as easy as possible. And this, when we do the sum, is just going to sum to epsilon. So we know that, at most, the outer measure of this set is equal to 2 epsilon. But I could have picked epsilon to be anything I wanted it to be, right? This holds for all epsilon bigger than 0. Right? So if the size of this set is less than any positive number, right, it must be that it's at most 0. Okay, if it's at most 0, but also it's at least 0 because we required it to be non-negative. So since also this guy is automatically non-negative, so we can say, well, this set has Lebesgue outer measure equal to 0. Okay, which again is something we could not do before with the Jordan content, with the Riemann integrals. This set was inaccessible to us, but now, without too much work, we can get a handle on the size of this set. Right, and I mean, I guess there's nothing so special about this as compared with any other countable set, right? Anything that I could put in a one-to-one correspondence with the natural numbers, I could basically do this trick on and get the same result. Okay, so suddenly we've done a hard integral in some sense, right? We've integrated the function 1 over this domain. We haven't quite defined what an integral should look like. But what we want is this to be consistent with the kind of definition of the integral we come up with. That will come up to saying, well, if the set takes up no volume, and the function is some bounded function, then we should get 0. So that's the integral that we've seen pop up occasionally last semester and this semester. What happens if we integrate over a crazy set like this, or we have a function that's jumping, depending on whether we're at a rational or irrational point. This is getting us towards that. Well, this is just the rationals. I haven't said what the size of the irrationals is yet. And we don't know that yet. The reason we don't know that yet is because we don't have additivity yet. right? The rationals and irrationals are disjoint, and we know that the union of them gives us the complete interval. So right now we know the rationals measure 0, the complete interval measure 1. We'd like to say, well, the irrationals fill up the rest of the space, they must have measure 1. But we don't have that yet because we don't know that disjoint sets, we can just split up their measure. Actually, we can't quite yet. There's a catch. Okay, so one more property we'd like is this one, additivity. We'd like to say that if these two sets are disjoint, then the measure of their union is just size of A plus size of B. It turns out this isn't true for the Lebesgue outer measure defined on all possible subsets of R, for reasons that I'm not going to get into because I have a couple classes to give you a brief overview and do an actual integral. You can look up the Banach-Tarski paradox if you like, where basically you take a unit ball, then you decompose it and reconstruct it into a new ball that has twice the volume, to two new balls that both have the same volume as the original ball. And you can create bizarre sets that let you do things like this. No, we don't, I mean, this is like alchemy or witchcraft or something. We don't live in a world where this usually happens. So maybe we want to restrict to sets that look more like what happens in the real world. Although if you could figure out how to do that, just start multiplying what you have for free. That would be nice too. So we're going to just say we can handle these sets that show up like this. We're going to restrict ourselves to nice sets. The good news is irrationals will still turn out to be a nice set, so we didn't just lose the nice result that we have. So we need to restrict our domain to nice sets. Okay, essentially we're going to restrict our domain to sets where this works for us. So let me define one property we want. We're going to talk about a measurable space. Okay, is a collection. Okay, so a family A of subsets of the reals. So not, you had this capital X before, which was all subsets. Now we're going to look at limited families, such that, here are some things that we want. Basically we want this family, so minimal things we want is that this family of sets is closed under taking complements and taking countable unions. Okay, so if a particular set lives in this family, then its complement lives in this family. If I take two sets from this family and take their union, the union still lives in this family of sets. Okay. What's that?
Are these called Borel sets?
Are these called Borel sets? Yeah, so this is now leading into the concept of a sigma algebra, and what I was going to try to avoid saying today, but there you go. So the basic concept, right, is just that if we have a set, then we have its complement. Okay, that's something we'd like. If we have the rationals, for example, if we're living in, say, between 0 and 1, we have the rationals. We'd like to also have the irrationals. So things you say about the rationals will give us information about what's left over. Okay, and if we have a bunch of sets, then we'd like to also have their union.
Those are, for one, those are script A's, right?
For one, this is a regular A and this is the script A.
Okay.
Yeah. So A is a particular set. Script A is my family of sets. Okay, and indeed, a family having these properties is called a sigma algebra. All right. Okay, there's lots of ways of doing this. You know, for example, I could take as my collection, well, I should always have the empty set, and okay, I'll take the set of all reals. And then maybe I choose to take, say, 0 to 1, minus infinity to 0, 1 to infinity, minus infinity to 1, 0 to infinity. And you know, all possible unions have to be in here. So what else? Minus infinity to 0. Union with 1 to infinity. You know, I can have small collections of sets that have these properties, right? Start with a few things, make sure all the complements are included, make sure all the possible unions are included, and I get something that's a sigma algebra, right? So just restricting like this isn't enough to give us what we want, because we don't want small collections. We want like as large a collection as we can have. So what we're going to try to do instead is to limit to this, basically the biggest collection of sets that has the properties we want. Yeah.
So, I mean, we can only take the null set and R.
We could take the null set and R, sure. That would be a very small collection of sets. Right, so there's lots of very small collection of sets. There's lots of, you know, we could take all possible subsets. That would still be a sigma algebra because all the unions, all the complements are included. So what we want is kind of the biggest sigma algebra we can have. It has these properties. You know, we wanted to have these properties because we want measures. You know, if we know the measure of a set, we should know the measure of its complement, for example. We want these properties, and then we're going to write down the properties of the measure that we really want, which is we'd like to have this additivity property in there. If we have disjoint sets, then the measure of the union is equal to the sum of the individual measures. So this is what we want. We start with a measurable space. Okay, and now we're going to have a function that we call a measure. So mu takes as its domain now not all possible subsets of R, but just the subsets that live in this family. Okay, and we're going to call it a measure if well, the empty set should have, again, 0 measure. We want, I'm going to rephrase things a little bit. This will still be consistent with being an outer measure, but will be a little bit stronger. So positivity. Positivity came out for free before from comparing sets because the null set is contained in any other set. So 0 is less than or equal to the measure of any other set. I'm just going to rephrase this a little bit. And then additivity. Okay. So if we have a bunch of disjoint sets, then the measure of the union is equal to the sum of the individual measures. Okay, and again, this automatically gives us the properties of an outer measure, but it gives us a little bit more. It gives us this ability to work with joint sets. Now, the Lebesgue outer measure, okay, it automatically satisfies this and this. It has the subadditivity property. It doesn't automatically have this property if we let our domain be all possible subsets of R. It just doesn't. Again, for reasons that this is advertisement to go study more analysis, more measure theory, I guess. Obviously, I'm not going to talk about why. Except to say that life gets weird when you start working with uncountable sets. Okay? Finite sets, we can handle. Countably infinite sets, even then, our intuition still kind of works. No big deal. Uncountable sets, things get hairy, yeah.
I kind of feel like the Lebesgue measure is like an extension of the Jordan measure.
Yeah, that's a reasonable way to think about this. This is an extension of the Jordan measure. And that's what we want. We want this on nice, well-behaved sets. We'd like this to give the same answer as the Jordan measure gives us. And indeed, it will turn out that it does. But this is indeed an extension in the sense that, but we can do more. We can handle more than we could do before, but it collapses to the same thing on well-behaved sets.
So does that mean that we can say like every Jordan measurable sets are Lebesgue measurable?
Yes, every Jordan measurable set is Lebesgue measurable, and the measures will be the same. They have the same value. That's absolutely right. But the converse is not true. There are Lebesgue measurable sets that are not Jordan measurable. For example, the rationals. Okay, so this is a result, which again, I'm not going to really fully prove, but I'll state. So this is a theorem by Carathéodory that tells us how to characterize, we start with all possible sets, but we can't do it. So what is kind of the biggest collection of sets we can come up with that gives us all these properties we want, that we end up with a measurable space, right? It's closed under complements and countable unions, and now it gives us additivity. So this is the statement, let mu be an outer measure, okay, on the reals. And let script A be the family of subsets of R with this property. Okay, so A lives in this family if, I'll state it and then talk about it a little bit. If the measure of S is equal to the measure of S intersect A plus the measure of S minus A for all possible subsets of the reals. Okay, so what this means is, and this is important, we want to test if A is in our measurable set. If A is a set that's Lebesgue measurable. We have a test for it that doesn't depend on comparing it to other things in this collection because we may not know. This test depends on comparing it to all possible subsets of the reals, which, okay, is anything. Okay, if this is true, then mu is a measure. Mu is a measure on R. Or let's say on script A. Right, so we say, here's my set A. We've drawn it high dimensional, I guess for effect, but we're actually doing the reals here, but this works high dimensional. And we want to know, is this set a Lebesgue measurable set? Well, to do that, I have to pull out every possible set S, and, okay, which could be nice sets, or they could be pathologically weird sets. Okay, we know that even if it's a pathologically weird set, this number is still defined, right? It may not be defined in such a way that additivity holds as we compare with lots of other things, but it's still a number. So this is our set S. And then what we're going to ask is that the size of this set is equal to, okay, the size of this plus the size of this. So we have some kind of, so the collection of Lebesgue measurable sets are sort of the sets that force additivity to work. By definition, we've said we're forcing additivity to work in here, even if we compare it with other sets. Now I take this set and compare it with some other weird set, and it may not force additivity. Okay, again, this is something that one can prove, and it's not that awful to prove, actually. It's reasonably straightforward. You have to verify that you've got closure under complement and unions. And then you have to verify these three properties hold for all your sets with that property, and it's actually relatively straightforward calculations to verify that. Okay, what we're going to say is if we live in this set, we're Lebesgue measurable. So if a set A lives in the collection coming from this theorem, it is said to be Lebesgue measurable. And then you can start to go through the list and start to verify that some of your favorite sets are Lebesgue measurable, and start to verify that some of your other favorite sets that were not Jordan measurable do live in this family. So for example, suppose that A is a subset of the reals with Lebesgue outer measure equal to 0. We looked at one such set, of the rationals living between 0 and 1, and we said really any countable set would have this property. Well, then we can check that if it has measure 0, it automatically satisfies this property, so it lives in our family of sets where we can start to do countable unions and complements, and we have additivity, right? So let's check this. We have to, what do we have to check? We have to check that this is true. Okay, so let's see. The first step, so we're going to do this as two inequalities. We'll check that this is less than or equal to this, and we'll check it's greater than or equal to this. So one direction is to say, let's write this as, let's write S as just the union of these two pieces. The union of the intersection and the union of the set difference. Well, this is not a measure, but it's an outer measure right now. Outer measure already satisfies subadditivity, right? So for free, we get this direction. It doesn't matter what A is. It doesn't matter what S is. This is just free. Okay, and that'll be the case whatever set we're checking. So that direction is always free to us. It's the other direction that is going to require a little bit more work, but not much work here. Okay, so let's start with these and try to pin down what's going on here. Well, let's see. Let's start with this one. What is the outer measure of this set? Yeah. 0. Yeah, why? It's a subset of A, right. So we know that this is a subset of A. We know that A has measure 0. So by comparison, again, we got outer measure. That means this has measure less than or equal to the measure of A. Okay, so this guy goes away. Okay, by the same token, this guy here is a subset of S. Right, so by our comparison result, we can say this is true. Okay, that's a property of an outer measure, which we have. And that means if I add these two things together, well, this guy is 0. This guy is bounded by the measure of S. And I've got the other direction of my inequality. Right? So it's a little bit complicated to state this, but in many cases it's not that hard to check it actually, for a lot of reasonable sets. Okay, so we got this direction of the inequality, we got this direction of the inequality, so we must be able to conclude equality. Right, and it didn't matter what S was. Okay, so we have that condition. So if Carapadoria is right, that means we've got a Lebesgue measurable set. It means this set plays well with additivity. Okay, so we say great, A is Lebesgue measurable. Okay, so for example, this guy that we did, the rationals between 0 and 1, is actually a Lebesgue measurable set. So not only can we come up with a number when we stick this inside our function mu, we can always come up with a number. It's a number that's kind of meaningful, that will play well with other sets. Okay, another example is we could take unbounded intervals. Okay, so let's see what happens here. What do we? One direction is always automatic here, right? Subactivity gives us that for free, so we don't have to check that. So once again, this guy is just automatic. Right now, we need to try to work out the other direction, which is a little more work. Well, there's some value of mu of s. So we're going to go back to we need the definition of the Lebesgue measure here. Right? You know, the definition is implicit here that the definition gave us leads to mu equals 0, and then we go from there. And we use the definition here to show that this had measure 0. So let's go back to the definition. It was defined as an infimum of a bunch of things. Okay, so that means we can always find a collection of sets of these intervals, infinitely many maybe, that cover S, right, and get us within a distance epsilon of that infimum. Right, that's what the infimum means. We can always get arbitrarily close. Okay, so we know that for all epsilon bigger than 0, there exists some collection of intervals such that S is contained in these intervals. Now, let me call this IN. And if we add up the length of all of these intervals, this can get us within a distance epsilon of our infimum. Right? We can never actually be less than the infimum, right? But we can be less than the infimum plus epsilon. Right? And automatically, this is bigger than the infimum. So this direction is automatic. But the key is we can come within epsilon of this. So I'm going to break this interval up a little bit. So let me take my interval IN. All right, and we're going to try to, let's see, how do I want to break this up? We're going from A to infinity. So let us say that this overlaps somehow. A is in here somehow. Okay, and I'm going to break this down into the parts that are less than A and the parts that are bigger than A. So this interval I'll call Kn, and this interval I'll call Jn. Right, one of them could be an empty set, that's fine. And I'm also going to put a little bubble around A to make sure it gets covered. Okay, so let me write down the definitions of these. So Jn is just the part of my interval that lives above A. Kn is the part that lives below A. And K0 is a little bubble around A. Okay, and I'm going to start intersecting S with all of these different pieces and see what happens. So what do we see? The S intersection with A to infinity is contained in, well, S is contained in the union of all of these guys. Right, so if this is my different IN, and now I'm intersecting it with just the part that's bigger than A, I'm just going to get Jn. So this is really just the union of all of my Jn's. Infinity to infinity, that should be A to infinity. Okay, so this is my interval, right? I had to do S intersection with this. That's one of the pieces that comes up. And then I have to do S minus this. So S minus a to infinity. Well, that's the part of S that's back here, less than or equal to a. So it's the part that's going to intersect with all the k's and with this k naught to make sure we include a. So this is the same as S intersection minus infinity to a, including a. And this is contained in all of these kn's. Here I started at n equals 0 to make sure that we also have an interval that covers a itself. Okay, and we can write down the length of all of these intervals. Right, we're supposed to sum the length of the IN interval. Well, that's just the length of Kn plus the length of Jn, and missing one point doesn't change the length of the interval. So the size of IN is broken down, and the size of K naught, of course, is 2 epsilon. It's just a little bubble. Okay, so now what do we need to do? We need to add up the measure of this plus the measure of this and try to compare it to the measure of S. So we need the measure of intersection plus the measure of the set difference we know which direction we want the inequalities to go, right? We already established that the sum of these two things is bigger than or equal to mu of S. Now we need to establish that it's less than or equal to mu of S. Well, this set is contained in this union. So the measure of this is going to be bounded by the measure of this, which by subadditivity is bounded by the sum of these intervals. Sum from n equals 1 to infinity of the jn's. Okay, same deal here. My set difference is contained in the union of all these k's. So the measure of my set difference by subadditivity is bounded by the measure of this union. And again, by subadditivity is bounded by the sum of the length of all of these. Okay, well, let's combine these. For n equals 1 to infinity, we know that jn plus kn, the length equals in. And then we also have to include the length of our little k naught, our little bubble, which was 2 epsilon. We have a goal. We're trying to get towards the measure of S. So here, what I have, the sum of the length of the intervals, and that is closely related to the measure of S. We know it is because these aren't just any old intervals. These are intervals whose length gets us within epsilon of that infimum, and the infimum is the measure of S. Okay, so that was what's key here. These are special intervals that get us really close to the infimum. So this, what we know before, is that this is less than or equal to the measure of S plus epsilon plus another 2 epsilon here. And that's what we need, right? This holds for all epsilon greater than 0. So we can say, great, therefore, indeed, we actually have equality here. had this direction. We now have this direction. And that tells us that this set that we started with, this interval from a to infinity, is measurable. Okay, and from there you can start building up a lot of other things. What this is actually a useful building block. Obviously, this is going to be the same argument. And now you're really in business. We've identified a couple of non-trivial things that are Lebesgue measurable. Now, we know that our collection of well-behaved sets is closed under complements. It's closed under countable unions. A here, of course, can be any real number we like. So now we have power to start taking whatever complements we want, whatever unions we want, and we get new measurable sets. So for example, if I want a bounded interval, well, I just need to write this somehow as a combination of complements and unions of sets like these, or of sets that have measure 0. So we can do that. We start with all the reals, and then subtract out everything we don't need. What don't we need? Well, we don't need anything from minus infinity to a. All right, good. That's a known measurable set. We don't need a itself. Okay, singleton, that has measure 0. Like all countable sets have measure 0. So this is a known measurable set. We don't need b itself. Okay, again, that's a singleton, measure 0, known to be measurable. And we don't need anything from b to infinity, which is, again, a known measurable set. So what is this? This is nothing but, okay, in here we have a union of a few measurable sets, which is measurable. Then we take the complement of all of that, still measurable, so this is measurable. All right, this is made up of unions and complements of measurable sets. Okay, so we don't have to go through all of the gymnastics, right? We had to do the kind of the gymnastics once to give us a building block. So we did the work to get this as our building block. And then once we have that, we can start coming up with all kinds of combinations. Similarly, AB is measurable. Okay, now similarly, we can come back to the irrational numbers between 0 and 1. Well, once again, we can start writing that down as a mixture of complements and unions of measurable things. And so similarly, let's let B equal, say, everything from 0 to 1 minus the rationals. So these are the irrationals now. And this is going to be measurable. And we can come up with this measure by additivity, right? So by additivity, the measure of this set, the interval from 0 to 1, which is the union of the rationals and the irrationals, which are disjoint, is going to be just the measure of the rationals, so it intersects. Well, we know the length of an interval. The length of an interval is 1. We know that this has measure 0. So now we have that indeed the irrationals, there's a lot more of them than the rational numbers. We knew already, I guess, that they were uncountable, but now, in fact, there are so many of them that they take up space. The rationals, even though there are infinitely many of them, they just don't take up space. The irrationals, there's a lot of them. All right, and again, this is a set that we couldn't measure with the concept of Jordan measure. So I'll stop here today, and then next class we will try to turn this into a definition of an integral, and then next week, Thursday, we'll talk more about the final exam.